Evaluating definite integrals. I just want to show you the notation that is used when we are evaluating an integral from a to b, and it's this notation right here, where the capital F is the antiderivative, and then we use the bar from a lower limit to b. And that means that we take the higher limit minus the lower limit. So looking at our first example, remember your rules that you can split this polynomial into each term. So in essence, this would mean this. And then again, using your rules, you can pull those multipliers out. But the antiderivative of 3x squared is x to the third. And the derivative of e to the x is e to the x, or the antiderivative. And this last one is 3 over x. And we know 1 over x is natural log. So this is 3 natural log of x. And that's from 1 to 3. If you wanted to read earlier with the fundamental theorem of calculus, it shows how the family of antiderivatives and that constant c relates. In that constant c, it doesn't matter what that is, which is why we don't use it when we're doing definite integrals. And then you just substitute in. So we have 3 to the third minus 2e to the third plus 3 natural log of 3 minus 1 to the third minus 2e to the 1 plus 3 natural log of 1. You get this first whole part is negative 9.875. This inner part is negative 4.437. And you might want to just double check and make sure that you get those numbers when you put it in your calculator. Okay, so I have a problem here for you to try based on that. Integral 1 to 3 of 4x minus 2 e to the x plus 5 over x dx. I'm going to separate so you know what the two parts were. The first part with the upper limit and the lower limit. Okay, let's look at this with substitution techniques. So the first technique I'm going to show you is just the pure substitution, where we let u equal x squared plus 10, du equals 2x dx. So I have a 2, and I don't have a 2 up there, so this is 1/2. Integral of 0 to 5, 1 over u du. And we know 1 over u du, antiderivative of that is natural log. So this would be 1/2 natural log of u. Substituting in what I let u equal was x squared plus 10 And now I evaluate that from 0 to 5. Substituting in. So you get 1/2 natural log of 35 minus 1/2 natural log of 10, and that equals 0.626. Okay, so I have a problem for you to do. Evaluate integral 0 to 1 of 1 over 2x plus 4 dx. Okay, I want to show you another way of doing substitution, and it's not that you have to do it this way, but I just want to give you that opportunity. So when I say u equals, and then I do du, and I set up now my, let's do u to the 1/2 du. Instead of using and doing our antiderivative of this and then using our -4 to 1 by substituting back in, we can now find out what our t or our u values would equal. For instance, my upper limit is 1. So if I kept the variable u, my upper limit would be 4. And then my lower limit would be 5 minus -4, which would be 9. So that I could now make this from 9 to 4 of our u, and then I don't have to substitute back in or anything. So I add 1, which is 2 over 2, so it's 3/2. I need to divide by that, which is the same as multiplying by 2/3. And then this is right from 9 to 4. It's just another method. Again, you certainly don't have to do it that way. Oops. Just an option. So you get -16/3 minus -18, which equals 38/3, or 12.67. So you have one to try either method. It does say substitute directly in using the method that I just did, but you certainly don't have to do that. And this is the